Here is a basic shunt motor with its starting box. In the starting position, the circuit to the rotor windings is closed through a series of large resistance coils. As the lever of the switch is moved, rotor speed and CEMF build up gradually, and the resistance coils are subsequently cut out until running speed has been reached. The lever is held in the fully open position by an electromagnet. If for any reason the power should fail or the field coil open, the electromagnet becomes de-energized and the lever is returned to the starting position by spring action. Just as in DC generators, DC motors seldom use permanent magnets for the field. Instead, electromagnets are used. Like with a DC generator, field windings are constructed in several ways. Each type of winding has special characteristics, special values, and specific uses. The series wound motor has good starting torque or turning force. Torque depends on armature current and on field strength. Since field strength is proportional to current, the high starting current before CEMF is developed affects torque as the square of the current. The motor begins to turn, attempting to develop enough CEMF to completely oppose the applied EMF. The load prevents this, acting to control the speed of the motor. But if the load is suddenly removed, like in the case of a broken belt, the motor will build up speed trying to develop more CEMF until it destroys itself. The shunt wound motor has less starting torque, but it is less dependent on load for speed control. In the shunt wound motor, the field coils are connected in parallel directly across the DC input terminals. The starting torque is not as great as in the series motor, since field strength is not affected by armature current. The speed of a shunt motor is fairly constant under conditions of changing load. As more load is applied, the speed of the armature decreases. This decreases the CEMF and increases the current input. The increase in current input boosts the coupling between the field and armature and increases the torque, causing the motor to resume approximate running speed. A sudden reduction in load will not damage the motor because the field current is independent of rotor current in the shunt wound motor. The desirable characteristics of both the series and shunt wound motors can be achieved in the compound wound motor. In order to obtain good starting torque, the series field is used. When running speed has been attained, a centrifugal switch cuts out the series field and cuts in the shunt field. It is now a shunt motor, and the speed regulation is good. Compounding provides good starting torque and good speed regulation. This allows for efficient operation and minimizes the possibility of damage to the motor. Now for a quick summary. The operation of all rotating electrical machinery is based on one simple principle: the generation of an EMF. The principle is used in the construction of a simple AC generator. The generator output E, or instantaneous EMF, equals B, strength of field, times L, length of the conductor, times V, velocity of the conductor. But because the movement of the conductor in the field is actually circular, we must also multiply with the sine of the angle formed by the lines of force and motion of the conductor in order to arrive at the EMF. All generators are basically alternating current generators, and produce AC internally. The basic AC generator becomes a DC generator when a commutator is attached to the conductor. Each commutator segment rotates with its respective conductor, producing a direct current. This current, which is a pulsating current, is made smoother by the addition of more magnets and more loops. Sparking in a generator is sometimes caused by a shift in the neutral plane. This can be corrected by adjusting the brush position. Or by the use of interpoles and compensating windings. Current for field windings may be supplied from an outside source, in which case the generator will be separately excited. Or the current may be a part of the generator's own output, in which event it is called self-excited. Generator field windings are constructed in three ways. Series wound, where the field windings and the armature are in series. Shunt wound, in which the field winding is in parallel with the armature and the load. And compound wound, in which the best features of both the shunt and series wound generators are combined. Voltage regulation in the series wound generator is poor. In the shunt wound generator, voltage regulation is fairly good, but current regulation is poor. Compound wound generators provide stable voltage under changing loads. This output is normally most desirable. Motor action is the opposite of generator procedure. In a DC motor, voltage is applied to two or more loops in a magnetic field. This causes polarity in the loops. The interaction of this polarity with the polarity of the field makes the loops rotate. This is the basic DC motor. When the conductor of the motor is rotated by an applied EMF, it also generates a counter-electromotive force. According to Lenz's law, this generated CEMF must oppose the applied EMF. As in generators, field windings in DC motors are of three types. The series wound motor has good starting torque, but since its only governing factor is the load, the speed regulation is poor. If the load is disengaged suddenly, the motor will race to destruction. In shunt wound motors, with the field coils connected in parallel across the DC input terminals, the starting torque is not too good. But since the field current is independent of the rotor current, the speed regulation is quite good. The compound wound motor combines the best features of both types. It uses a series section for good starting torque. Then it switches to a shunt arrangement for good speed regulation. DC electrical motors and generators are at the heart of much military equipment. A proper understanding of them is therefore important.